So welcome back after a few, 1 week and a half maybe without a proper lecture. Today we're gonna get back and talk about variational autoencoders, and the idea is to switch to generative modeling. So far we've been talking about, in the entire course, about what we call discriminative modeling. And starting today, we're going to switch gears a little bit and talk about generative modeling, which is the general idea of modeling the distribution that generates the data so we can generate new samples. Okay, so long time ago, we were talking about multimodal learning, specifically with transformers. We saw how to model images as sequences with visual transformers. We saw that it splits an image as patches, and then pretty much uses the same architecture to learn visual data as sequences. And then we saw that since transformers are this very generic architecture, we can build these multimodal models just by somehow tokenizing different types of data as sequences. So if you can represent image as a sequence of tokens, and if you can represent text as a sequence of tokens, then you can just encode text and decode image, or encode image and decode text, or encode audio and decode image. So we can make this very general framework of machine translation, if you want, to translate one modality to another. Okay, and then we saw these examples of text to speech and text to image, but you could build potentially any type of translation model from different modalities. And then at the end, very quickly, you talked about CLIP, which is this very cool idea of learning embeddings for images and text in a combined space. So if you get the embedding of the word dog, that embedding would be close to the embedding of an image that is an image of a dog. So then this is very cool because it helps you making any different types of applications. Like you could just do a zero shot classifier just by having a text of like an image of a dog, and then you get this embedding and compare with the embedding of the image you're trying to classify. If that's the closest match, then you have an image of a dog. So, and CLIP is actually under the hood between in these models that we use to generate images today. So any model that takes a prompt, not any, but most models that takes a textual prompt to generate images, they somehow use CLIP under the hood to correlate the prompt to the images you want to generate. So it's a very interesting modular way of separating the problems. So you get the prompt, there's text, you map this to the CLIP embedding space, and then that helps you generate an image of that text you're trying to produce. Okay, but today we're gonna actually keep talking about generation, because last time we were talking about generation in some sense, but not explicitly. When we were talking about transformers, we were generating, let's say, an image from a text, or maybe a text from an audio. So it is a generation task, but it's way more constrained, because you have a target. Like you know that, for example, when you are doing, let's say, speech recognition, you have a speech in audio, and then you know that what is a correct translation or transcription of that audio. In generative modeling, we are less constrained in a way, because we want to learn a distribution of images, let's say of cats. So we can generate new samples that somehow look like the examples in the data set. So that's the overall the goal of generative modeling. I'm gonna just quickly recap that we already actually studied generative models when we talked about RNNs and transformers. If you think about it, language modeling is a generative model, and I'm going to explain why. And then we're going to switch to image generation explicitly, which probably some of you have already seen these topics, but from now on, actually from today till Wednesday, we're going to be mainly talking about image generation. But most of these models are pretty general. They can be applied, in theory at least, they can be applied to other sorts of data. But we're going to talk about one particular model today, which is Variational Autoencoder. And to talk about Variational Autoencoder, or VAE, we should first talk about autoencoders, which are just, because VAEs, they are based upon autoencoders, and it makes much more sense to first talk about this, autoencoders, than VAEs. And as part of the discussion, we're going to see how or what type of losses we use to train these models and whatnot. So first of all, what is the difference between discriminative versus generative models? So far we've been mainly talking about discriminative models. In other words, these are classifiers or regression models, because here what we want is we are given a set of data points, and we want to find a function that maps the feature vector x into a label y. And we can see this as a kind of a splitting problem. We need to find somehow a decision boundary that splits the data, right? This is different than generative models. So in generative models, we still want to learn a function, but we want a function that approximates the distribution that generated the samples. Okay, so here I'm kind of like showing these ellipses here as they were maybe the areas of a normal distribution, even though it doesn't have to be a normal distribution, but just showing you that now we don't want to find a decision boundary anymore. We want to model a probability distribution more explicitly, but we want the probability distribution that we assumed that generated the data. So somehow we're going to have to add or assume that the distribution looks like something, and then try to approximate that function. Right? There is no magic here. I have to define what a distribution is, and then try to find parameters somehow that give me that distribution. And there are different types of algorithms to do that. So we already saw autoregressive models, which by autoregressive models, I am generalizing this idea of language modeling. It's pretty much modeling a sequence or modeling the next token based on the previous ones. This is the general definition of autoregressive models. Today we're going to talk about variational autoencoders, but there's also generative adversarial networks and diffusion models and others, but these four are perhaps the most popular these days. Okay. So in previous lectures, we already talked about one very important kind of generative model, which is autoregressive models. As I said, this type of model assumes this distribution. It assumes that the data comes in a sequence, and the next element, xt, is a function of the previous t-1 element. Okay? And then we saw that we can model this either using an RNN, or you can use a transformer. There could be other networks to actually model this type of model. But we already seen, and these are actually very important generative models. Okay? And they can actually be used to generate text in natural language, which is perhaps the standard application. But we saw like those cool ideas of generating like source code in a programming language, or even image generation if you think about image as a sequence of pixels or patches, right? Music generation, speech, and others. Okay? So these are pretty general models. But okay, we've seen them, we covered them very deeply. So I want to switch gears a little bit and focus on image generation, but I don't want to see image as a sequence. I want to see image as a data point, just one unit or one example. And that's the formulation we're going to look into in the next lectures. So somehow I want to model a distribution of pixels that I can sample from to generate new set of pixels that look like cats, for example. So if I train my my model in a data set of cats, right? I want to be able to generate new types of cats. Or if I want to, maybe I want to generate new fake faces, right? So I could train a model in the data set of faces, and then I can sample from this distribution now and just make fake faces, right? Or I can even do better. Maybe I can have a data set of multiple types of objects. Maybe I want to train an image generator on ImageNet that has 1,000 classes, right? And somehow I want to control my distribution to say, oh, generate me an image of a bicycle, or generate me an image of a train or something, right? This is a slightly more complicated idea because I have to condition on the label itself, but that's the kind of models we're going to be talking about in this next 2 lectures. And these days, these are the 3 more popular models: variational autoencoders, generative adversarial networks, and diffusion models, all for generating images. Okay, they can generate all sorts of data as well, but they're very good at generating images. Okay, so let's first talk about an autoencoder, because in this lecture we're going to focus on variational autoencoder. But what is a basic autoencoder? So an autoencoder is a very cool idea from deep learning, and it's not a very recent idea, to be honest, but it's this idea of having an encoder-decoder model designed to learn to compress and reconstruct data. Okay? So first thing you should look at is this input vector here. This is just a vector x, right? It has 1, 2, 3, 4, 5, 6, 7, 8 dimensions. And if you look at the very end of the network, I'm calling this, x hat here. This is the same vector, but reconstructed. Okay? So I want to reconstruct my input data, but there is a twist, right? I want to do this in a compressed way. So look in the middle here. I want to reconstruct my data by first compressing the input into a much smaller vector of 3 dimensions, for example. Because if I haven't there, the problem would be trivial and useless, right? If I didn't have this bottleneck, then I could just use the identity function. The goal here is not to learn the function itself, is to learn these compressed vectors here. So obviously, this task is going to produce me some sort of lossy result. But as long as the loss that I get in this reconstruction is not that bad, then we can actually, this compression version is very, very useful. Okay? Same if you think about any compression algorithm, right? Most of them are lossy algorithms, like the JPEG image compressor, right? It reduces the size of the image, but the visual aspect of it still remains very close to the original data. And that's very useful because it helps us saving a lot of space. And also, like if you want to transfer this over the network, it's much shorter data. So I mean, this is one of the most motivations for compressing information, compressing data. And in fact, you can use autoencoders for that. But what is cool about this as well is that by compressing the dimensionality of the input data, we force our model to learn intrinsic information from the data. So the model has to just keep here whatever really matters, right? And it has to learn some sort of structural representation, maybe looking at the neighbor pixels or something. So it has to look around and see maybe, well, I have to drop some information, so I have to somehow like combine stuff around me or something to make some sort of like still be able to reconstruct my data. So let me just formalize this a little bit better. So we start with an input vector x, and we pass this through kind of a few input layers, if you want, called the encoder. Okay, and we're calling this the encoder because eventually we're going to have this bottleneck here that is a middle layer in the network that has the minimum dimensionality. And we're going to call this a latent representation Z, right? And then we can see this second part as a decoder. Even though technically it's the same model, right? But because it has this very particular structure of it starts with a large input and it goes down, and then from that moment, from the middle moment on, it starts growing back again. So this is called a decoder, and the output is the input, but reconstructed from the Z vector. So it's a very clever idea, and very simple but clever. And the key aspect is this bottleneck layer here. Okay? And this is what makes it work. Because we're interested in this Z representation here. Okay? Which you can use for all sorts of things. Not like I mentioned compressing data, but you can use this just to learn latent representations that maybe are easier for linear models to classify, right? Maybe you can use an autoencoder to get a vector out of an image, and then use a logistic regression to classify that image or something, right? So you can use this for many different applications. But the intuition here, the idea is like how could you use this for generating? So keep that in mind today, that the goal that we are trying to get is being able to generate images or other types of data points. But let's focus on images. Okay. So I'm not getting into generation yet. Let's just apply this autoencoder idea for image compression. Okay. So imagine you want to learn an image compression algorithm like JPEG. So what you could try to do is let's think about MNIST data set here just for simplicity. You would have a single channel image that is 28 by 28. And this, by the way, is a very tricky example because I'm not sure if it's a 7 or a 3. But anyways, you get an image of a digit, right? And you want to pass this through a now CNN encoder. We know that CNNs, they already have this bottleneck structure, right? They keep reducing the feature map and making it deeper, right? So you could get in the middle here a Z representation that is, let's say, 7 by 7 by 32 or something like that. So it's a smaller representation. We started with a 28 by 28 by 1, and you could just get to a 7 by 7 by 32. But then you could have a decoder to use also a CNN somehow, right, to map this feature map Z back to an image. Okay? And spoiler alert, this should be in animation, but well, we haven't seen how to upsample an image yet, right? In CNNs, we saw how to downsample images. Right? They start very large and they keep decreasing in size, but we didn't see how to do a backwards operation or the inverse operation, which is upsampling. How do you take the small feature map and scale it up, right? And the answer is transposed convolution. Okay? There is this operation which is, you can think of it as the opposite of the traditional convolution. Okay, and this is how it works. So instead of sliding the kernel over the image, we kind of going to do this reversely. We're going to slide the image over the kernel. So here's an input image that's 2 by 2, and I have a filter of same size, which might look weird, but just for the sake of the example, it's easier to look at. Okay? The goal here is to take this image and make it larger. Okay? So this operation does the following. It takes this input value 0 and multiplies by all the numbers in the filter. So 0 times 4, 0 times 5, 0 times 6, and 0 times 7. And then we're going to put this here. And the output will be 3 by 3 because we have a stride of 1 here. I'm going to show you why. So this first operation is just literally taking this 0, 0 element here and multiplying like a normal convolution by each element of the filter. And then you would give a 0, 0, 0, 0, right? Now we go to the next input, which is 1, and you're going to slide it again through the filter. So now 1 times 4 is 4, 1 times 5 is 5, 1 times 6 is 6. So see how I'm sliding this cell all across the filter. Okay? And then I get 4, 5, 6, 7. Okay. And then, note here that from this output to this, there is a stride of 1 because I moved 1 step to the right to get this 4 elements here. Okay. And then I go to the input, this is 0, 0, 0, 1, 1, 0 now. Right? So this is 1, 0 is equals to 2. So 2 times 4 is 8, 2 times 5 is 10, right? 2 times 6 is 12, and 2 times 7 is 14. So okay, so probably you got the idea now. Oh, and then now it's 3 times 4, 12. I move the stride here by 1. So I start now putting the numbers here. So 3 times 4 is 12, 3 times 5 is 15, 3 times 16 is 18, and finally 3 times 7 is 21. So now what I'm going to do is all these blank cells here will be zeros, and I just sum the four matrices. And this is the resulting output. It's a 3 by 3 output. Okay. So now you saw that we started with a 2 by 2 image and it grew to a 3 by 3. Okay. And this is a stride of 1 type of transposed convolution and no padding. So the only thing that changes if you had a stride of 2, for instance, is you would, when you're producing the results, you would move your output 2 steps instead of 1. So the idea is the same. I'm going to multiply this 0 by the filter, so I get zeros here. But now when I move to the next one, I'm going to just skip 2. And now I have this 4, 5, 6, 7 over here. Okay. So that's just a strided transposed convolution. And it's interesting here that we got no overlaps at all. So when you're working with transposed convolutions, you have to think about the filter size and also the strides and padding. But since this is not the goal of this lecture, I don't want to spend like do exercises and whatnot. I just wanted to mention to you that this operation exists, and it follows the same idea as convolution. It's just kind of the opposite operation. But let's not worry much about it. I just want to make sure that it makes sense and you can use it to increase the dimensions of your images. And ideally, we want to do this as we do with regular convolutions. We want to do this in steps. Maybe halving or doubling the size of the input every layer or so. Not just one by one. That would be it would require too many layers to actually increase, right, the image. Okay, and padding, it's funny because it seems like a hack, but intuitively, when we added padding in the regular convolution, we want to normally we want to keep the output the same size of the input. So we add padding to the input to keep the same size or even increase the output. So if there is a way, if you want to increase the size of your feature map, you can actually add lots of padding to your input. That would make the output bigger than the input. So that could be one way, actually, of making you're doing upsampling. But this is more common and effective. But here the idea is the opposite. Padding is actually, we use padding to reduce the size of the image. So if you say you have a transposed convolution with padding 1, this means that you're going to literally just drop this surrounding like rows and columns. So you just literally remove them. Your final output will be just 4 here. Okay? There's a 4 here. So all these numbers here would be just thrown away. Okay. And it's, here, imagine if I had a 5 by 5 image, then I could have padding of 2 that would just remove the 2 rows and columns of the borders, or the outmost. I wish we had more time to discuss this and maybe play with this idea. And I'm going to point you to some readings so you can see how this is used. But this operation is very common in like image autoencoders, but also GANs. In GANs, you will see that you're going to have the same need of somehow upsampling a feature map. And then we're going to use this idea as well. Okay, but the real focus of the lecture is VAEs and how to generate images, and I want to get there. We haven't talked about generation so far. But this is an important part to get to VAEs. So when we are training an autoencoder, we want to compare the reconstructed output, x hat here, against the original input, x. And there's a few ways of doing that, but basically we want to compute an error pixel by pixel, right? And most people use MSE, just mean square error, right? So here's our mean square error, but now I have just a sum over the height and the width of the image, and I'm comparing pixel by pixel. For example, this pixel ij here against this pixel ij here, and I'm going to move all of them and compare one by one. So, and because this, we can see colors as values between 0 and 1, people also use binary cost entropy. Because these values can be seen in a range from 0 to 1, and then it would work as well to use BCE loss. Okay? But MSE is more common. But both would work in this case. Okay, this is all straightforward. There's nothing really fancy here, right? It starts to get interesting now. So what could you do with just basic autoencoders? So there is one very popular type of autoencoder called denoising autoencoder, which does what the name suggests, right? Is that we want to train an autoencoder to reconstruct the image X, but not from directly from X, but from a noisy version of it. So we will by hand introduce some noise. And normally you use a normal noise here, or a normal distribution, a standard normal distribution. By standard I mean 0 mean and 1 variance. So then see, this will be your corrupted data. And now you still apply reconstruction loss, so you still make your decoder generate the original input, but now it has to learn to remove this noise here, because the loss is compared against X. But what I give the model is X tilde. So the model receives this, and I compute the loss against the original X. And this is really cool because adding the noise here, what it's doing is it's forcing the model to learn some sort of internal structure of the data. Because, for example, to fix this certain pixel here, the model probably has to look at its neighbors and see, oh, this is an edge of a tree, so there should be a white pixel here, not a gray one. Okay? So adding the noise is a way of making the model or forcing the model to look around, and somehow it's just a constraint. I'm going to add a constraint to the model to force it to learn the structure of the data somehow. Okay? And on top of this, you could actually use this as an industrial application because, well, you might have corrupted image that you got from the internet, and you could fix these images by denoising them. Or think about if you take an image or a photo at night, right? You get a lot of noise in your camera because it's a low quality camera. So if you look at the pixel, it's very blurry and looks bad, right? So you could use some sort of autoencoder to actually fix dark images to get more high quality image, right? But the key intuition here in theory is just to add some constraint to the model. Because again, if you don't have a constraint or you don't have a bottleneck, then there's nothing much the model can or you're going to just let the model learn the identity function, that's useless. So you have to pose some restriction. Okay, just to motivate a little bit more, there is another idea which is very similar, and we've seen this before, which is masked autoencoders. And it's just a different way of posing a constraint to the model. Is that instead of adding noise, we're going to mask some patches of the image. By masking, I mean literally removing that part of the image. I take a patch and take it away, right? I make a hole in the image, or many holes. And then I want the model to fill in that hole, like complete that back again to me, right? And this is similar to what BERT was doing. Right? In BERT, or even Word2Vec, right? When you did the CBAL model, we take a word from the middle and then you use the context to predict the middle, right? And here's a similar idea, okay? Here I want to predict back these gray areas. These gray areas here are the patches. So I took them away, and now I want to reconstruct the original image, but now from this broken, let's say, image, right? Or masked image. And there is this recent work here, 2021, that uses a transformer to do that. Okay, so this is just an example to show you that there is multiple ways you could pose this problem of autoencoding. It's a very general idea. It works very well for different applications. And here what they do is they use a VAT. So they take this original input X, they slice it into patches, and these patches are highlighted here in these dashed lines. And then what they do is they literally remove the patches that are masked. So they take these away. They don't even add that mask token. In the BERT model, they have that mask token that somehow substituted the patches. Here they don't even have that. They just fill in the image as it was formed by this patch, then this little patch here, then this white one, and so on and so forth. But because it has positional encoding, it knows that these things should be in this certain order. And then it uses a regular VIT encoder, but there is another trick here. They use this very small VIT decoder. So they add another constraint to the model, which is it starts with a large embedding space, and then the decoder is constrained, so it has to learn to work with much smaller dimensions, right? And then this really helps learning very good representations of images that then you could use to classify, for example, for image classification or for other stuff. This is actually a very good idea to pre-train the VAT. So if you want to pre-train a VAT in a very large data set, right, you could use this. And then you can fine-tune it later for image classification, for example. Okay. So yeah, here adding this masking is just another way of imposing a constraint to the model. Okay, so again, this is kind of like going off the road a little bit, but it's all cool work, and I think really brings or kind of like shows the potential of autoencoders. And I presented to you like like this first denoising autoencoder is from 2008, and there's still people working with these ideas. Okay, so it's very useful tool to have in your belt. And thinking about deep learning architectures and training the procedures. Okay. All right, we are getting there now. So how could you use an autoencoder to generate data points? So here's an idea. We could try to decode a random vector z. Now it's a feature map, but let's say we randomly generate a feature map and just pass it through the decoder. Right? Since the decoder has seen many examples, I'm just picking a random one. Hopefully, it should generate me an image, right? Because if this latent space here is interesting enough, or if it has learned interesting properties, then any z value that I put here should give me an image, right? Well, that's cool, but this doesn't happen if you train an autoencoder. So this image here that you see on the left, it's a plot of the MNIST data set right? Or it's an autoencoder trained on the MNIST data set. Each color here is a digit type. So you can't see it there, but the yellow is 9, right? Green is 8, purple is 7. Okay, so these are images of digits, and each color represents what digit they are. And this is the latent space of an autoencoder trained to reconstruct the MNIST data set. So here, for instance, you have a 1 here. So this is the group, the cluster of the 1s, right? And here's the little 1. And the purple here is the cluster of the 7s. What would happen if you try to maybe get this point in the middle of them and use it as a Z, right? There's no point in there. I haven't seen any point in that space from my data set. So the decoder would give me garbage, right? Because this space is not even defined, so I don't know, the model hasn't seen anything in this area. What the model kind of tends to do is to cluster the images because that helps reconstructing them. But it doesn't guarantee continuity or anything like that. Okay? And that's the motivation of variational autoencoders, is to learn a more useful and well-behaved, let's say, latent space. So you want our latent space to be a little bit better than this. So it's not broken. It doesn't have these spots in between areas here that could be undefined images. Okay? So that's what I just said, right? Examples are typically clustered in different regions of the latent space. And if you try to decode, let's say, if you try to decode a random, let's say, Z to generate an image, we might get garbage. Okay. So you want to fix that, and that's what the variational autoencoder is going to do, fix this latent space. Okay, so let's focus on this discontinuity problem, right? The way that the VAE is going to fix that is by learning a distribution or probability distribution P explicitly. And even though it could be any type of distribution, in practice people use a normal distribution. So they approximate a normal distribution. So we have two parameters, a mean and a variance. Here is actually standard deviation. Okay? So we're going to build a model that learns these two parameters, mu and sigma. And that's the output of the encoder now. So the input is the same. It's just an image of a digit. But the encoder is going to output a vector full of means and another vector full of standard deviations. Okay? So then what I'm going to do is now sample a Z vector. Oh yeah. I'm going to sample a Z vector out of this distribution. Here, let's just keep track of some things. The size of these vectors, it's a hyperparameter. I'm using 4 here. Okay? And each row is a distribution. It's a separated distribution. So this mean here, 0.1, is associated with this 0.2 standard deviation. And this 1.2 is associated with 0.5. So when I'm sampling the Z, I'm going to sampling per row. Okay? So like this. Z1 here would be sample from this distribution, a normal distribution with mean 0.1 and sigma 0.2. So I would get maybe 0.28 or something. Right? And then the second dimension we would sample by this normal distribution with mean 1.2 and standard deviation 0.5. Right? And then I probably would get 1.65 or something. Okay? And so on and so forth. Is this clear? Is there a question? So also here, just to keep track of some other stuff, the Z tilde here, this sample vector, obviously is going to have the same dimensionality of mu and sigma, right? Because I have one sample value for each of these rows. So this has to have the same number of rows as this. And what is cool here, we're going to learn these two vectors. So they start randomly. They start at random distributions. And then at every forward pass, we're going to sample a bunch of these Z tilde vectors, okay? from these current distributions. And then after every weight update, these weights are going to be changed towards a better distribution somehow. And that's part of the loss function. But what we want here is to start, imagine like we start 8 different normal distributions that are random, and somehow I want to adjust them based on some loss function. And that's what the VAE is doing. Okay. And then the decoder is exactly the same. It doesn't change. The only change we have is in the encoder, specifically in the output of the encoder. Instead of outputting the Z directly, we're going to output 2 vectors that represent multiple normal distributions. Okay. Again, feel free to stop me if this doesn't make sense. Okay. So in an autoencoder, my Z vector is pointing to just one point in latent space. Because I have these independent points, I'm going to have by design, I'm going to have a discontinuity in my latent space. Unless I see like infinite amount of points, right? But it's because I have a limited amount of training data, there will be, and each Z is associated to each example in the data set, right? There will be a discontinuity by design. So the way you're trying to fix this is now I'm learning these 2 vectors, mu and sigma, and or you can think of this as having one of these per label, let's say. Imagine these red points, they will be sampled just from the digit 1, okay? Because that's what happens. Because of the sampling procedure, right, what happens is, let's go back to the previous slide. Because the Z tilde is sampled, the same input X will be mapped to different Z's. Is it clear? So if I do a for pass in my network, the more I do this, the more I'll cover this surrounding area here. Okay, and the mean is exactly the center point. And the standard deviation here is the area that I'm going to cover when I sample. But that's what's happening now. This is the core of the VAE, is that it doesn't model a point anymore, but it models regions in space. Okay? And we're going to learn multiple of these regions. And here the mean value controls the center of this region, and the sigma controls the area of the region. Okay. So because these nearby points refers to the same class, right, we get by design, right, because I always get the same image, 1, I know it's a 1, right, so it's going to model the ones sample around that area. If I get another one, it will actually do a very similar procedure. But the way it does this is also because of the loss. Okay. All right. So what we wanted, ideally, is a space that looks like this somehow. Each color here represents, let's say, a digit, right? And we want a continuous, like, we want to cover the latent space with regions that have overlaps among them, so it doesn't have any holes in it. And if images have shared features, let's say a 7 and a 1, all of them have, let's say, the center, the bar right in the middle, I want them to have these overlaps, right? So this would be ideal. Because let's say if this was a 1, so if this area represented 1s, and if this area represented 7s, maybe I wanted these like images in between to look like those images you don't know if it's a 7 or a 1, right? Kind of something in between, actually. But that's not what happens if you just try to reconstruct your data. If you use a reconstruction loss, pure and simply, what could happen is something like this. the key point here is there. If you just let the model learn the mu's and sigmas, there is no boundaries. There's no limits to the mean and the means and the sigmas. So it could just put them anywhere you wanted. Like for example, these ones could be here, right? These threes could be here, because I'm not constraining the means and the sigmas. Remember, each mean is a center. So if there's no constraint on where I can put the center, the model can put it anywhere it wants, right? And the same for the size of the region, the area. You could just minimize it to have less variance, and in the infinity, it can become an autoencoder. Because if it points to the same point, then it's just same as doing an autoencoder, and this is useless. So what we are getting, if you don't constrain, again, we can get very different centers, like means, for different classes, and that would cluster them apart, and that's useless because, again, I would get these holes in the middle here, and the model could minimize sigma, for example. So how do we fix that? And the idea is very simple, actually, but very elegant. So the idea is to add what we call a Kullback-Leibler divergence, which is a very complicated name, to something that is not that complicated. But we call this for short KL divergence, okay? And we're going to add this term to the reconstruction loss. So just in general words, KL divergence is a metric is a distance metric between distributions, okay? I'm not going to get into details here. I'm going to put this in the notes of the lecture. So if you're interested, we can discuss that because you can see the math. I'm going to have some math on the slides, but not the entire math. But KL divergence is a formula. Let me show you for you. It's a metric, very common in machine learning and statistics. It's a metric of distance, or it's a metric to compare two different distributions. So if I have a distribution P and a distribution K, so that we denote this by divergence KL, right, of P compared to Q, right, you're going to sum over all values of our distribution, so all classes you can have in your, let's say if it's heads or tails, right, you have just two x's here in your universe. And then this is the probability of x log probability of x over probability of qx, right? So this metric is going to give 0 if the distributions are exactly the same. So it's a distance metric. If the distributions are exactly the same, this results in 0. If they're very different from each other, this value is going to be high, okay? So if I have these two distributions, P and Q, I can apply this formula to compare them and get a single value that tells how different they are from each other. And I'm going to compare this value against this. So P of 0 would be this bar, and Q of 0 would be this bar. So I divide one by the other. And then take the log, right, and multiply by this value, which is P of x. And then I do this for the second outcome, which is 1, right? And then I take now P of x is this for 1, and then Q of x is this value. I divide one by the other, take the log, and multiply by this value. Sum of the previous one we got, this is going to give you one scalar, one value, that is the distance between these two distributions. Okay. I'm going to add in the slide with this math, with the proper names and terminologies. Yeah, so we're going to get there. So this is the original autoencoder loss. It's just an MSE between x and x hat, which is the reconstruction loss. This is the original. So we're going to just simply add a term to this loss. Okay, so the VAE loss is going to be the MSE between the reconstructed image and the original image. So this is the part that comes from here. Nothing changed. Plus what I'm going to call the KLD, or KL divergence, between our learned distribution and a standard distribution. So we want all these regions to be centered at 0 and have one variance. So this is what forces the overlap. They will be centered at the same part, but they'll have, I mean, this is not guaranteed. I'm not going to guarantee that they will be exactly at 0, all of them, because they're going to fight each other, let's say, during the training procedure. But that's the ideal, is to center them around 0 and have them with different, so the variance 1, sorry. So this is imposing a constraint. You can actually see this as a regularization term, because I'm constraining my parameters sigma and mu to the normal standard distribution. Okay, that's it. Okay, that's exactly it. That's the only thing that VAE does. And it's a very simple fix. As I said, we want to compare the learned distribution sigma, mu sigma against a distribution with mean 0 and variation 1. So yeah, that's what I just said. This loss encourages the encoder to distribute all encodings evenly around the center on the latent space. Okay, and if you solve, so if you get that formula of KLD, right, and solve it for these two arguments, you're going to get something like this. Right? This summation here is over the dimensions of that vector. So this is each distribution. So it's just the sum of all these distributions. Okay. So I'm not showing the full math here, but if you want to know, like this is the result you would get. We are basically just comparing two normal distributions here. And finally, let me show you how now it looks like. So this is the new learned latent space. See how the center here is 0. Most of the data points are centered around 0. This is 0, and this is 0 here. And now I don't have holes in this whole area here. All of them are centered here. Okay? And I still get these clusters. So I still get the yellows here. I still get the purples here. There is some overlap between yellows and purples, right? And in this case, purple is 7 and yellow is 9. Oh, wait. I think this is 1, actually. The 9 is the darker one. So this is brighter yellow is 1. It's right here. So it has this overlap with 7. It makes a lot of sense because they are very similar to each other. And so on. So this is the original space we had with the autoencoder, and this is the learned space we get with the VAEs. Okay? So now we don't have these holes here anymore. Okay, let me... Yeah, so properties. Right, the latent space now maintains the similarity of nearby encodings, which means by these clusters. So it still has these clusters, which we had here, right? So we have this locality still represented, but globally, right, they are all packed around the 0, the center of the space. So this gives us a very interesting embedding. And let me show you some cool applications you can do with this. You could interpolate in the latent space, because now you have this continuity, which means that any point here is going to be decoded in a real output. So you can play with this. Let's say you get an image, and this comes from this paper here, autoencoding. No, sorry, this is not the paper. But these images come from a paper that does exactly that. So you have a sketch now of a cat and a sketch of a pig, right? And you can take the Z using a variational autoencoder. You can take the latent representation of this image and the latent representation of this pig image, and then you can just interpolate between them. You sum and divide it by 2, and what you get is just this little pig here with a face of a cat. So interpolating in the latent space means interpolating semantically in the real space. And this is really, really a very, very cool property for real-life applications, right? So for example, if you now start moving from Z1 towards Z3, you would get your image of the cat getting closer and closer to the image in the middle here. Okay? And the same on the other side. Okay? You start kind of like merging the two images in these two directions. And you could do this kind of algebraic representations in latent space. So you can get an image of a cat, first get an image of a pig with a body, subtract of an image of a pig, and then some with the face of a cat, and then you would get a cat with a body. Okay? And this always you do in vector math. So it's very interesting for creative applications. Okay? Same here. So that's what I had for today. I wanted to make sure the lecture was recorded and in enough time. So I can take questions now, and we can actually take any offline discussion. Let me